Hello, class. Today we're going to be talking about mutually exclusive events or non-mutually exclusive events and how to find the probability when we're given those contexts. Please keep this in mind on Thursday, or actually, no, that's not, okay, never mind. On Friday, we're going to be taking a lesson quiz. So, what we have been talking about so far in terms of probability of events and these things, non-mutually exclusive events and mutually exclusive events, and how to deal with those probabilities will be on the quiz. It will be very short, um, and that will be taking place 2 days from now. So please keep that in mind. For today, please write down these formulas here. We have talked about mutually exclusive events before. That simply means that they have nothing to do with each other. So in a Venn diagram situation, we have these circles, but they're not overlapping. So as you can see, the probability of one of them does not impact the probability of the other. That's what is simply what it comes down to. And this right here, which we call a complement is something that is the probability of the opposite thing happening. So, for example, let's say that there's a basketball shooter who's averaging a 0.7% making free throws. So when we say the complement of that, as you can see in the formula right here, what it says is 1 minus probability of that event A happening. The probability of event, let's say, making free throws, if you do 1 minus 0.7, what we get is 0.3%. I'm sorry, not 0.7%. That should be 70%, right? So, or in decimal value, that would be 30%. So what this comes down to is that it's the opposite value, or the probability of event A and the complement should always add to give you 100%. So the probability of that particular player not making free throws, that would be the context, would be 0.3 or 30%. That's what is called to be the complement of the probability of A or event A. Now, mutually exclusive events, the formula up at the top. I don't know why I can't zoom out here. Okay. All right, so probability of event A and B are mutually exclusive events. Then the probability of A or B happening would be probability A plus probability of B. Now, the probability of A and B happening at the same time would be just 0, because there is no mutual place in which both of them are happening at the same time. So therefore, that is not simply going to happen whatsoever. Let's say that I go over a couple of these questions here. I believe that I went over these questions with you in the past, where I was talking about mutually exclusive and non-mutually exclusive events. So I'm going to skip these guys all the way down here. And I'm also going to be talking about probabilities of non-mutually exclusive events. So if an event has a mutually exclusive event happening, in other words, if there's an overlap, in which we'd like to call it, that means that the probability of A or B happening is probability of A plus probability of B minus probability of A and B happening at the same time. This is the formula that I would like you to write. So right now, currently, what you should have are 3 formulas. 1, probability of non-mutually exclusive events, somewhere this. So write this somewhere in your notes. And then write this somewhere in your notes. And then write this somewhere in your notes. Okay? All right. So once you have those 3 formulas written down, let's take a look at some of the examples, and that's what we're going to be doing for the remainder of today. Let's say the context is given to us like this. So, a jar contains 12 green marbles and 8 violet marbles, total of 20 marbles. A marble is chosen at random from the jar and then replaced. The key word here is replaced versus not replaced on part B. Another marble is chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes from the second marble chosen? Okay, so let's draw the situation. we have a jar, okay? And there are 20 marbles here, okay? We'll pretend that's like 20 marbles here. And we are picking one out of random. Now, the probability of you might choosing green would be 12 out of 20 because there's a total of 12 greens out of 20 total marbles. Or you could be picking violet marbles, that's a chance of 8 out of 20. So you pick one, and then you replace it back into the jar. So when you pick it again the second time around, because we're talking about another marble is chosen, that's the second time around. During the second time, does the probability of the first impact the probability of the second time? Well, the probability of choosing the first marble, the second marble being green is 12 out of 20, which is still the same as the previous one, as you can see. This one and this one's the same. And then the probability of choosing the violet marble is still 8 out of 20, which is the same thing here. So what's my answer to the first question? We say no. Does the color of the first marble chosen affect? No, it does not. So what does this mean? These two events, this event and this event, which we call that mutually exclusive. The probability of the first does not have anything to do with the probability of the second. Then take a look at B, and then it's not replaced. Think of the same situation, but it's not replaced. So what that means is, from the jar, you pick either green or violet, but then on the second time around, you do not replace it. So I am not going to replace it here nor here. I still have the jar, and the probability of the first one, that's still the same. However, because you picked one marble out from the jar, how many total marbles do I have in the jar as of currently? That's right, it's out of 19. So that certainly impacts the probability of the second one. So the probability of the second one does get affected by the first. Okay, so I want you to see how the probability of the first can impact the probability of the second depending on the situation. The word here is the one that you want to focus on is the word replaced. Very, very important stuff. Let's take a look at another one. So try it. There are 10 cards in a box, 5 black and 5 red. 2 cards are selected from the box one at a time. A card is chosen at random and then replaced. A card is chosen at random and is not replaced. Does the color of the first card chosen affect the probability of the second card? Does the color of the first card chosen affect the probability of the second card? How would you be able to write the answers down? Pause the video and then let me know. Well, if you just rewind back about 60 seconds ago, you could probably get the answers to these right away, right? Because we are talking about 10 cards, 5 black and 5 red, so both of them have an equal chances. But if it's replaced, you know it's not affected. If it's not replaced, then it is affected because your probability of the second time around, will be out of 10, it will be out of 9 because one card is chosen and it's gone. Okay, so another formula, actually this part we are not going to be doing here. Actually, the probability of events happening here. Let's see. Actually, for this one, I'm going to give you the formula, and then what we're going to do is we're just going to talk about it. I'm going to give you several questions related to this, as well as the previous selections there. So, instead of writing 4, the complement question was really not much to do. So, let's talk about probability of independent events. Independent events, what that means is same thing as saying not happening with each other, but there is a slight bit of a difference between independent events versus mutually exclusive, and we'll go over that more tomorrow. But what you need to know is that if you determine that if two events are independent events, which means they have nothing to do with each other, still nothing to do with each other, that simply means that the probability, if we're talking about the and situation, that those two happening simultaneously at the same time, you just have to multiply them. So, for example, there are 12 possible results from the independent events rolling a number of cube and tossing a coin. So, rolling a cube is 1 out of 6 because there's 6-sided die, and the flipping a coin is it's either heads or tails. So it's going to be 1 out of 2. So if we're talking about, let's say, getting a 4, like this one, and getting heads, like this one, then the probability of those two happening at the same time will be 1 out of 6, because that's getting a 4. Getting a heads is 1 out of 2, and you just have to simply multiply them. If you multiply them, you get 1 out of 12, so the event of that specifically happening is 1 out of 12, which is shown for you also right here. So the basic formula that I want you to write down in your notes is this. If A and B are independent events, I cannot zoom in here. If A and B are independent events, then P, A, and B happening at the same time is probability of A times probability of B. Okay. Now, let's take a look at some of these questions here. Alex cannot decide which shirt to wear today, so she chooses one at a random. The probability of rain today is 40% or 2 out of 5. What is the probability that Alex chooses a yellow shirt and it does not rain today? So we have two situations. Number one, we have the selection of shirts that we can wear. Number two, we have a rain. Now, are these two events independent? The answer is yes. Some of the students I know for a fact, but what if it's raining and you prefer to have a specific color of shirt? No. What you wear as in terms of color of shirt, this is talking about color of shirt, has nothing to do with the rain. If this was like a raincoat and this, like if we're talking about coats, for specific weather you want to wear one specific type of clothing more than the other, I get that, but this is just colors. So they have nothing to do with each other, okay? Let's establish that first. Rain, color, clothes have nothing to do with each other. So what is the probability that Alice chooses a yellow shirt? Well, yellow shirt is 2 out of 4, isn't it? That's 1, 2 out of these 1, 2, 3, 4. And it does not rain today. Remember the complement question? The complement formula? If the probability of raining today is 40%, that means that the complement, which is not rain, is 60%, which is 3 out of 5. So what is the probability that Alice chooses yellow shirt? And the magic word here is and remember the previous formula says that if we're talking about the word and, we're going to simply take those two probabilities and multiply. So take those two probabilities and multiply, we get 12 out of 20. Reduce that and I get, what would I get? 3 out of 5. There we go. No, I'm sorry, that's not it, right? That's 3 out of 10. Yeah, that should be 3 out of 10. I'm sorry, why did I say 12? That should be 6. My apologies, that's 3 out of 10. What is the probability that Alex chooses a yellow shirt and it does not rain today? Or, it says or. So first of all, Alex chooses a yellow shirt and it does not rain. Well, we already found the probability of that. That's 3 out of 10. Or that Alex chooses a green shirt and it rains today. First of all, finding green shirt is 1 out of 4. Rains today is 2 out of 5. That those two are also independent events, so that's 2 out of 20, which is 1 out of 10. Now, the magic word here is or. We're talking about this entire event, and then this entire event happening. It could be either or. So what do? I take this probability and take the previous probability, and you add them. Magic word here is the word or. It simply means plus, and then and would be multiplication. I just want you to think of it simply like that. Of course, it depends on various different situations, but vast majority of the cases, this is the kind of a shortcut key that you guys would like to remember. So 1 over 10 plus 3 over 10 is 4 over 10. Reduce it, 2 over 5. Okay, so hope this video helped out. We're going to be talking about mutually exclusive events and independent events from some time onwards, and I want you guys to solve a couple of questions regarding those, and that's going to be it for today. Thank you and have a good day.